All right, well, hello everybody, and hello people watching later on the recording. I'm Dr. Daniel Raymer, and quite interested and involved in this project, and I would share something with you here, which is some thoughts for a manned Mars airplane. So let me just get right into it. When I first prepared a presentation and wrote a paper for this, I asked Bob Zubrin to do a haiku for me. And there it is, and I think it's quite nice. He'd never done a haiku before, but he decided to give it a try anyway. And that's the kind of attitude that's going to get us to Mars someday. So let me just jump right into it. First of all, just kind of a eye candy picture showing this thing landing on the Martian surface. A couple of people get out. You'll notice they have a big hemispherical clear dome in front, which is also the door, but they can look through that. And the guy who did this rendering decided it would be amusing to put the little Mars helicopter right next to it to show scale. So the Mars plane itself, it's an old idea. People have been playing with that since the 1970s. And it turns out it's not that hard to conceive of an airplane that will fly on Mars. You can do the math and get the wing big enough and get enough power for it. Previous studies that I'm aware of have all been looking at some kind of an explorer vehicle that gets sent from the Earth, goes through reentry in some kind of a shell back there. You can see that. And then unfolds itself and flies around for a while. And that's a neat idea. And I was briefly on the faculty at California State University at Northridge a number of years ago. And we had a student design project that designed and built a Mars plane. And here it is. And they're out in the Mojave Desert testing it. So it's certainly something that is possible and feasible. But again, it was an unmanned airplane to be launched from the Earth. And my thought is that eventually people are going to be living on Mars. That's certainly the plan. And when they're living on Mars, they'll be needing a way to get around, maybe for exploration or maybe to go from one Martian town to the next Martian town, hopefully someday. So I started thinking about that when I was invited to give an AIAA paper, and decided to do this as an AIAA paper. It's a presentation, actually. So anyway, I just started thinking about what would be required, what would be a good set of design requirements for a manned airplane that flies on Mars. And I decided the good old Jeep from World War II turned out to be a very good, very useful vehicle. Some people say it was one of the weapons that won World War II. In any case, so I decided that that would be a good starting point, as good as any I could think of. So 2 people or 500 pounds, kind of go anywhere like a Jeep. And a fair amount of range. The Jeep had 260 nautical miles range. That certainly seemed like a good number. I just wrote that down and decided to use it. In my design study, I'm assuming that there are already permanent bases on Mars, manned bases, and I'm assuming that those bases have lots of electrical energy. So getting energy isn't my problem. I'll assume that they have nuclear power plants or maybe huge solar farms if that's feasible. But in any case, we'll assume they have that, and we'll assume large pressurized buildings. Other people have talked about architecture of buildings. Well, just make sure you make one of them like a hangar, because I want to put together an airplane in that great big facility. Okay, so with that in mind, I put this design together, and let me start at the end and then I'll work backwards. So here's what it looks like in flight. Very big wing, of course, for electric propellers. And it gets closer. You can see the body pod there. It's coming in, ready to land. And it fires up some jets, some rockets actually. And it actually lands vertically on rocket thrust. And then it takes off vertically on rocket thrust, accelerates, and flies away. So that's the basic idea of this thing. Some more of the overall operational concept. And this is just Dan Raymer making up stuff, but I think it makes sense. First of all, it would be optionally manned. You really wouldn't need a pilot. 2 people could fly in it, and they can pretend they're pilots. And we might even give them a video joystick, kind of a game controller, so they can steer left and right and tell the system, okay, land here. But all the flying would be done by computer. And you could also fly it unmanned. Just put 500 pounds of stuff into it, push a button, and it flies where you want to go. We'll assume that it is fully charged from a ground source. The batteries are fully charged, and also rocket propellant is loaded using ground cracking equipment. I'll talk briefly, but it's a carbon monoxide / LOX rocket, and that can be cracked out of the Martian atmosphere. And I did the sizing to allow for 2 takeoff and landing cycles. So you take off, you fly out, you land, you take off again, you fly back, and you land at your initial base And that's all done without any further refueling. All right, so that's the basic idea. And I'm also assuming 2030 technologies, and 2030 is getting close at a rapid rate. Maybe I better make that 2040. Anyway, whatever it is, it's more advanced than we have today, but not crazy advanced. I'm just assuming we can do a better job at designing laminar flow airfoils, and we can do slightly better in terms of structural weight and stuff like that. No great big magical things in there. Okay, design drivers. I kind of made up a bunch of design drivers and some assumptions, and some of the drivers, of course, the atmosphere is ridiculously thin, so you need a huge wing and you need to fly fairly fast to get enough lift to fly like an airplane. You do have the advantage of the reduced gravity, so you don't need as much force to carry the mass. The weight is less because of the gravity. So in effect, you need about 23 times the total lift for a given speed on Earth. Another driver is the propeller tip speeds. The speed of sound is lower on Mars, and we're probably going to have large diameter propellers. So it's just one of these things to keep in your mind if you try to do a design of your own. I wanted a pressurized cabin, just like Jeff Bezos's vehicle. I don't want them having to get into spacesuits and spend all day with a helmet over their head. So pressurized cabin. I want an excellent field of view. You saw the bubble in front. Vertical takeoff because there aren't any runways, and the configuration needs to give pretty good ground clearance because we're going to land off base. We're going to land wherever we think there's a spot. So I want the wing and propellers and everything else high up off the ground, but I don't want the people having to climb down a ladder. And so you'll see how I saw that. Okay, assumptions and decisions, and these are things that would be great trade studies later. So don't ask, did you look at a helicopter? Because the answer is no, I didn't. I just made a guess. I did a vehicle that I think would work, and I'm pretty sure it does. There may be a better vehicle. There may be a better approach. Maybe a rocket-powered jump jet is much better than this. Maybe just a pod with some rockets and enough thrust that you just blast yourself forward and come and make a vertical landing, and that might make more sense than going to all the trouble of making wings. But I'm an airplane guy, so I did an airplane. As I mentioned, carbon monoxide locks rockets, and Jim French, who was well known in AIAA circles, co-author of the AIAA propulsion book, he's been working on this for a number of years. He worked with me and sized up a motor, rocket motor, and did the analysis of the propellant and stuff. I'm using his ISPs and his rocket motor rates. Jim wants to do onboard propellant extraction, and he really fought with me saying, oh, come on, Dan, stick this gizmo on it, and then when it's sitting on the ground, we can crack out more propellant. And I said, that's a great idea, Jim. We'll put that in the B model. So the A model is fully loaded with all the propellant you need, but it certainly is a possibility. But in terms of cracking out that propellant back at a main base, yeah, that's pretty easy. People will do it. Okay, anyway, part of the study is to find the technologies necessary. Okay, so this is the design I put together then. I started out wanting to come up with a pressurized shape that'll hold two people very efficiently. And what could be more efficient than basically an autoclave? So it's basically shaped like an autoclave, a round cylindrical piece, hemispherical cap on one end, and not shown here, there would be a cap on the other end, which is probably one of those insulated shapes. I actually added that to a later version of the design. Deliberately, the pod is low and the wings are high, and they're connected with a V-strut. Yes, I know it looks like the Starship Enterprise. That wasn't deliberate, and especially wasn't deliberately timed, considering what happened yesterday. But the reason for that is so that if there is a crash, the structural support of the wing won't puncture the pressure vessel. Basically, if you crash, you don't have the weight of the wing, but you have all the mass of the wing, the inertia of the wing. And if you do make a hard landing, I'm going to break away and not puncture the pressure vessel. So that was my reasoning. Also looks cool. Where the struts connect to the wing, there's a pod. The back of the pod has the pusher propellers, and it also has the rocket motors for vertical takeoff. They are angled away a little bit so you don't throw dust on yourself. And of course, helicopter-like landing gear. There would also be skids out near the wingtips just to hold the wing up. And I decided later that we really are going to need rockets out near the wingtips also for better roll control during takeoff landing. So that's the basic idea. This illustration, I should have mentioned, by the way, I should have mentioned on the first slide, I had an international team volunteer to help after the first presentation. And since they were all doing it for free, I didn't try to run them tightly and tell them just what to do. So they all did what was interesting to them. And I think it's great work. And all of their work is available in the paper that we did and also on our website. Anyway, so this shows a little bit better what the propulsion system looks like with batteries. These square flat boxes are batteries. And then there's the vertical takeoff jets there in those pods. I did a little bit of analysis here. Some of it was with spreadsheets and some of it was with my RDS aircraft design software. First of all, did a little bit of a trade study trying to figure out what kind of a speed I needed to be looking at. And when you look at vehicles with huge wings like this, you always think, oh, that's a slow vehicle. But in the Martian atmosphere, you have to go pretty fast. And so after looking at some trade-offs, I finally settled on 115 knots as stall speed. So that's size the wing. And that gives about 150 knots as a good cruise speed, where you start to get in the sweet spot for lift to drag ratio on the airfoil. So that seems to be about right. And I made an assumption of a 6,000 pound gross weight. And we kind of went through the sizing on that basis. And it looks like it's probably about right. Of course, with more funding later, should do a very detailed bottoms up sizing study. But that seems to be about right. When I started this, myself and a lot of other people thought the best way to land was a deep stall. To pull into a deep stall at a fairly high altitude, let it stabilize coming straight down, and then just before you hit the ground, turn on the rockets. And it turns out if you let it stabilize coming straight down, you're going pretty fast. There's not much air there, even with this huge wing. So you don't flutter down like a feather, you drop like a rock. And so it actually took a lot of time and rocket fuel to catch the fall. And it actually looks like it's better to fly in at a fairly low altitude, just over stall speed, and then basically pull back and slow down and shift to rocket lift. And that seems to be a better approach. Okay, did some classical aerodynamic analysis with my RDS software. It looks like somewhere around a lift to drag ratio of 40 should be attainable. That's a little questionable because of the very low Reynolds number. So it needs more work on that. We did some CFD in just a bit. I'll show you. I did do a weights buildup using a combination of some statistical equations that don't apply very well, and a lot of ratio analysis and some just Dan Raymer guesses. And certainly it could wind up heavier than this. I think it's about right. And I think I was pretty generous. Things like a wing weight of almost 1,900 pounds. That's not nothing. Anyway, all needs a whole lot more work. I did get some work done by the international team, which I'll show you in just a minute. Based on those numbers, I ran out and found a total range of over 1,000 nautical miles. Half of that, 500 out and 500 back, which is well in excess of my 260 goals. So I felt pretty good about that. At a reasonable vertical climb velocity, although we don't have to climb very high, just high enough to clear mountains and such. So it seems to work, meets stated requirements. One of the volunteers did a dynamic analysis of the takeoff, taking off vertically to about 30 feet straight up, and then beginning to accelerate forward using a combination of propellers, and there's two extra rocket motors in the back of the body pod. So that combination accelerates you, and then by the time you're at about 200 feet, you're just over stall speed. You can shut off the vertical thrust engines and fly away on wing lift. That looks like it works. And there's a whole bunch of graphs that I've shown you before. Felix Finger did some CFD and also some airfoil design and did some analysis. It looks like getting in that vicinity of lift to drag ratio over 40. In fact, he got over 50 at a fairly high lift coefficient, and that's wing only. So that knocks down to only 40 when you put the rest of the vehicle into account. And he also designed a number of airfoils and came up with this as the best one. Again, a whole lot more work is needed. This was a volunteer group. And I'd love to get lots of funding to do this in detail, but I think the volunteer group got quite a bit done. Okay, another volunteer, Arturo Gomez, did structural design as shown here, and quite a bit of finite element structural analysis based on some estimated loads that I gave him, and found you get a lot of deflection on the wing, which is to be expected because you've got that heavy body pod in the center, even though I spread that load out a little bit using those struts, but still it's quite a bit of deflection. But it's okay, as long as it's taken into account. and did a weight analysis and came up with 400 kilograms. So that was less than the weight I had estimated, but this doesn't include all the details and fittings and that kind of stuff. Okay, pressing on, there was a couple of volunteers who took a look at the interior arrangement. And one of the first questions is, well, Dan, why do you put them both side by side like that? And the answer is because it's roomy and comfy. And that's what I did. But you certainly could stagger them, as shown to the right here, and either tighten up the pod quite a bit or give them more room for stretching out. And these are going to be 5-6 hour flights. So kind of nice if they can stretch out and go to sleep and this sort of thing. We also did an analysis of the weight of the body pod itself. There's closed form equations in all the textbooks. So based on the loading conditions that I gave him, it seems like the body pod weight, and he came up with about 390 pounds, including insulation. So it's a little bit more than I was using, but not by much. And did some design. There's actually 2 different volunteers who did interior design, and I like them both. So we'll decide later. But this is one of the designs, taking advantage of the staggered arrangement as we discussed. And looking from the front when the door is open. In this case, these guys are wearing pretty normal looking spacesuits. The other rendering I showed you before, they're wearing like mechanical pressure suits where it's actually just tightly squishing you physically rather than putting air pressure in there. Okay, and another one of the volunteers did these renderings and showed heads-up displays sent onto the hemispherical dome. I kind of like these chairs, pretty cool, very lightweight chairs, and also these have the advantage of easily folding away. And I think that's a good thing if we're going to be using this for cargo sometimes, as well as for and flights. Okay, a little bit more of that arrangement. And actually, I think they're quite nice, nicely done. And then finally, we got some very nice renderings showing the vehicle in flight and a much better illustration of how it flies. So here it is coming in, and it's already starting to slow down. So we're transitioning the weight to the rocket thrust. We'll basically set the wing at CL max. There's no reason to go beyond CL max. Just set the wing at CL max. And let it slow down and start going more and more to rocket thrust. We could use the propellers to slow down more quickly, or we could possibly use them regeneratively and store some electricity back in the batteries and slow down also. There it is, coming in closer, and a couple of people inside that hemispherical dome. Rockets firing. There it is on the ground. 2 people out as we look at it earlier. So anyway, that's the basic concept. Obviously, this is an early look. Nobody needs it yet. Nobody is on Mars yet. I think I would call this more of an existence proof than anything else, although I personally think this design stacks up rather well. It looks like it works, but obviously, before you built this on Mars, which might not be for 20 more years, you do a whole lot more designs, a whole lot more work. Who knows, maybe it'll look something like this when somebody actually does its vehicle. So this was done, as I said, by this international team of volunteers, and the first slide showed who it is. If you go to my website, which is down here at the bottom, there's a page that has a whole lot on this project, illustrations, the reports by the volunteers who did a whole lot of work, way more than I could show you in 20 minutes, and some of the view graphs from previous presentations, and a longer video presentation that I did a while back. So it looks like it works. I think it works, and the purposes once we have people living on Mars, I think we're going to need something. Plus the fact I think it'd be a lot of fun to fly. So that's the presentation, and I'm happy to answer questions.
Okay, yeah. So I'll read the questions for you. So the first one is asking why you use the slugs per cubic feet.
Well, I was asked to give that first presentation by a US audience, and so I did it in British imperial units, and could be converted to metric at some point if need be. Was that the question, or did I miss something?
Oh yeah, that's that question. Okay, the next question. Okay. What do you think about bringing hydrogen airships back to life for Mars?
Airships back to life for Mars. Well, that's off topic pretty far. I've done a fair amount of airship stuff. It would be one heck of a big airship to lift very much weight. So I guess that would be my thought on that. There's not a lot of air there. You didn't see the Hindenburg flying around at 100,000 feet, which is roughly the equivalent air. And I guess the final answer is give me a contract and I'm happy to study it.
Yeah. Okay, the next is, what is the advantage to using a single airfoil that wide rather than a biplane design with half the width or even more layers?
Well, this comes up a lot. The biplane is very good for structure. You can make a nice truss structure out of it. And for that reason alone, it's something that needs to be considered. If you cut the span in half, you actually get much worse drag due to lift. And that's actually a common misconception about biplanes. What really matters is the total span loading, the distance between wingtips of the entire configuration, whatever it is, compared to the weight you're putting into it. So you don't get magic that way. But if you can stand a higher drag due to lift, then yeah, it's got some pluses. It also is going to have more parasitic drag, which is not a good thing. Anyway, it certainly should be part of the trade studies. I didn't do it because, like I said, I didn't have the funding to do a bunch of trade studies, but it would be in the design space of trade studies that you should probably look at.
Okay, another question is, what is the scale of energy difference between this and just paying the full energy budget of rocket transport?
And again, I did not do trade studies.
Yeah.
And if I was asked to do such a trade study, I wouldn't do it on a pure energy basis. I think fundamental physics often leads you astray in looking at things like this. I would design an alternate vehicle that would be, like I said before, kind of a jump jet. Make something that has a body pod much like this one, but has lots of propellant on board, and literally can simply rocket itself up and probably even out of the atmosphere and do a little suborbital flight, or maybe fly along horizontal again, another trade study. But I wouldn't do it just on an energy basis. I'd do a vehicle design study. I'd love to do it. It might be the right answer instead of big wings. I don't know.
Another question is, how do you solve stability and control without an empennage or empennage? Yeah.
It does have empennage, but the answer nevertheless is magic. But we love our magic. It does in fact have vertical and horizontal tails. And I didn't mention it, but I had to add the horizontal tails because the optimal airfoil had such a camber back towards the trailing edge that it would be quite unstable. And it would be possible, but difficult to artificially stabilize that. And of course, you don't want to fix it by moving the center of gravity, because then you deflect the trailing edge for control and you don't have the right airfoil anymore. So that airfoil led me to think we probably can't get away with a tailless airplane.
Yeah. And then we have a question from AltSpace VR. Is it possible for the person from AltSpace VR to answer or to ask their question?
I'm sorry, is it possible for them to ask me a question?
Yeah.
Sure, ask me a question. That's
yeah.
why I'm here.
Yeah, I don't know how. Okay, I'll just move on to the next question then.
But let me say this, if they want to contact me, go to my website, aircraftdesign.com, and at the bottom, there's a place you can send me an email.
Yeah, and we have about 5 minutes left. Another question is, could this flight plane be separated from the airfold and then travel on land to move around getting to destination?
Well, that's kind of a neat idea. Actually, looking at it, you could probably have a quick disconnect right there where the struts attached to the pod, and have some kind of simple little struts that come down out of the nacelles that would hold it in place. And then all you have to do is add wheels and a drive system and drive it away. The problem with that is you're adding weight. It would probably add enough weight that the whole system might be unfeasible just because of the extra weight. But sort of physically looking at it, yeah, maybe so.
Okay, another question is, given the high winds on Mars, did you or your team look at flight envelope, or does the rocket landing technique mitigate landing taking off in high winds?
Well, I saw that movie too, where the winds were blowing. Was it Matt Damon all over the place? I think that was in that movie.
Oh yeah, the
But
Martian.
yeah, right. But the air is so thin there, I'm not really sure that you get that kind of dynamic pressure, even if that wind's moving at 100 miles an hour. So what? You know, we're flying at 100 and what 100 and what was it, flying 150 knots, I guess. And the dynamic pressure is, I think it was 0.7 pounds per square foot. So that's not very much. So, and this is something I'm not really sure of, but looking at the air density, unless there's 1,000-mile-an-hour winds on Mars, I don't quite see how they're that much of a problem. I mean, you'd want to tie the thing down, of course, and as soon as you get out of it, you'd go out there with some, you know, screw-in tie downs and tie it down real good. But maybe I'm wrong on that, but I don't think it's going to be anything like it's on that movie. Okay,
another question I got is, what about seasonal air density, like how it is a problem with the helicopter?
Yeah, I totally ignored that. I just used like a nominal value. So basically what happens is if we're flying and the air is less dense, you're basically going to have less range on the vehicle, because first of all, you'll have to accelerate to a higher speed before you can shut off the vertical lift rockets. And then you'll have to fly the whole way at a higher speed, which means more electrical power consumption. It shouldn't affect the ability to actually fly vertically and go somewhere. Basically, it's going to turn into a range penalty. So you want to check that quick. If the air is not very dense that day, it might be like strong winds blowing in the wrong direction. You just don't fly that day.
And any thought to building a low-speed RC model?
Yeah, I'd love to, actually. If I wasn't busy on, you know, other things, I probably would. It'd be real fun. Yeah, and actually, you know, I'd love to get funding on this. I don't know if any stinking rich people out there would love to get involved and throw some money my way, but yeah, we could do a serious good design study of it and build a subscale model and actually fly it around and take this to the next level. Nobody needs it now, though, so that's kind of a problem. It doesn't solve any, you know, DoD problems or anything like that. So,
yeah. And have about 2 minutes left. Should the wing center have a breakaway seam so on crash land the struts fold sideways from fuselage?
Maybe. Yeah, a very detailed crash analysis would answer questions like that, and that'd be part of the real detailed study. What happens when you crash this? And you know, people that design helicopters, they're the experts. They do all this element analysis, stepping through the crash as everything deflects and all that stuff. We'd want to do the same with this eventually. Yeah, that's something to consider, definitely.
Yeah, and that's all the questions we have, and we have just about a minute left.
Great. Well, thank you all for listening. This was a lot of fun, and I hope you're all enjoying this conference. And kudos to Bob Zubrin and all his volunteer staff for making it happen. He's been working this a very long time. I've known Bob a very long time, and he's just been working real hard on this. Oh, I got enough time to say one more thing. Bob Zubrin actually won a talent show that I ran online for AIAA back in the height of COVID. So if you really want to see something interesting, go to my website and look for the AIAA online talent show, and you can watch Bob Zubrin in an amazing performance of Edgar Allan Poe's The Raven. It's really worth doing. And on that note, thank you all very much.